Now we will start the 5th lecture for this course, Artificial Intelligence. On this module on search methods that we started, today we will focus primarily on informed search methods. In the last class, we talked about several search strategies which use the strategies which are blind, that is, which do not use any problem specific information. We discussed depth first search, breadth first search, as well as iterative deepening search. Today we are going to finish that discussion after talking about bidirectional search, and then we will move on to informed search that use heuristics information. So in bidirectional search, we will discuss the algorithm, the time and space complexities, and then we will move on to informed search. We will talk about the algorithm A star, and before that we will talk about greedy search algorithm as well as uniform cost search, which are special cases of A star. At the end of this lesson, the student should be able to do the following. He should be able to understand what is a heuristic function. They should be able to design heuristic functions for a given problem. They should be able to prove that if A star uses an admissible heuristic function, it will terminate and produce an optimum solution. They should learn how to compare two heuristic functions as well as how to combine multiple heuristics. So in the last class, we talked about blind search methods, depth first search, breadth first search, iterative deepening search. Today we will talk about bidirectional search, and then we will move on to informed search. Subsequently, in the other lectures, we will talk about constant satisfaction, which can be modeled as search problems, and we will also look at adversary search, which is used for dealing with two-person games. So let's discuss about bidirectional search. In bidirectional search, in the other search methods that we have discussed, one starts from the start node, and then the search process explores the different nodes in search of a goal node. So the search branches out from the start state. In bidirectional search, in addition, one will also start from a goal node and search backwards from the goal node, trying to reach either the start state or one of the states which is reachable from the start state. So if one can reach from a goal to a state which is also reachable from the start state, then we have found a path from the start state to a goal state. The strategy which employs this is called bidirectional search. So we can look at this diagram which illustrates bidirectional search. This is the start state, and this is the tree which would be expanded if one starts from the start state and moves forward and one will be able to find the goal after examining these light gray states. In bidirectional search, however, one would start both from the start state and examine certain portion of the start state. At the same time, we will also start from the goal state and move backwards until the search frontiers of the forward search as well as the backward search meet. And if they meet at a particular node, we would be able to find a path from the start to the goal state. So, we see that it is possible that in bidirectional search, one may need to expand fewer nodes than one would if one carried on forward search. However, this may not always be the case. This is an example where the forward search is illustrated by this light gray envelope. So, this is the envelope of forward search and this is the envelope of backward search, and we see that these two envelopes do not really meet, so that these paths are disjoint. So, we do not save on expanding any nodes if we do bidirectional search. So, in bidirectional search, what we do is that we carry on the search process forwards from the start state as well as backwards from the goal, and we alternate these two phases. For example, we first expand some nodes in the forward direction and then expand some nodes in the backward direction, then again in the forward direction, again in the backward direction, and so on. Every time we expand a node, we need to check whether that node has been expanded in the other search tree. If it has been expanded, then we would have found a path from the start to the goal. That is, we stop when the frontiers of the forward and backward tree intersect. However, in order to do the bidirectional search, we have to start from a goal state. There are many problems where there are many goal states. It is difficult to decide which goal state we should start from. Therefore, bidirectional search works best if there is one goal state from the problem, which is easy to get to. The second problem that one might encounter in bidirectional search is how do we search backwards? For all problems, it may not be possible to search backwards. So, being able to search backwards means we have these reversible operators. That is, we can generate the predecessors of a state as well as the successors. In such problems, bidirectional search is helpful. Also, as I mentioned, we alternate from searching in the forward direction and searching in the backward direction, and every time we expand a node, we have to check whether that node occurs in the frontier of the other search tree. Therefore, we need, for bidirectional search to work well, we would need an efficient way to check whether a given node has already been expanded, right? If we take every node in the frontier and check whether it is same as the current node, bidirectional search, any advantage that we get by bidirectional search will easily be lost. And then for each of the forward search as well as the backward search, we have to select a given search algorithm. So, however, bidirectional search can sometimes lead to finding a solution more quickly. So, let us see what we would gain if we use bidirectional search. Suppose we have suppose this is our start state. and suppose this is our goal state, right, and let us say the branching factor is B and the distance from start to goal is D. So, we have seen that breadth first search, for example, would expand order BFS will expand order B to the power D nodes, that would be the time and space complexity. In bidirectional search, if we are lucky, the forward tree and the backward tree will meet exactly halfway. So, this is the forward tree and this is the backward tree, and if we are lucky, we have found an intersection of the forward tree and the backward tree, and therefore, we would get a path from the goal to this tree to this node as well as from the start to this node, that is, we will have a path from start to goal. Now, in the best case, this distance will be D by 2 and also this distance will be D by 2. So, the number of nodes expanded in bidirectional search would be 2 times B to the power D by 2, which is better than OB to the power D nodes expanded by BFS. So, in bidirectional search, in the best case, we will get 2 times B to the power D by 2 nodes. However, the space complexity is also B to the power D by 2, because we would have to store the frontier of at least one of the search trees. Like often what is done is we do breadth first search in one direction and DFS in the other direction. So, at least for one of the search trees, we must have a breadth first search type of procedure where we have a frontier which can be ordered B to the power D by 2. So, let us just go back and compare the different blind search methods that we have considered so far. Breadth first search requires time of B to the power D, space of B to the power D. It is optimum and it is complete. Depth first search requires time of order B to the power D, space of Bm, where m is the depth of the search tree. It is not optimum, it is not complete. Iterative deepening search has a time complexity of B to the power D, space complexity of only B into D, where D is the length of the cheapest solution. It is optimum, it is complete. Bidirectional search, when it is applicable, it might have a time complexity of B to the power D by 2, space complexity of B to the power D by 2. It is optimum, you can show that, and it is also complete. However, in some cases, these complexities, unless you have a very efficient way of checking with the frontier of the other search tree, there could be more overhead involved in trying to check if a node is there in the search tree. Now, we have so far considered search trees where we start from the search start state and unfold the tree that we get. Now, it is quite possible that the search space is more like a graph and not a tree. That is, from the start state to a node n, there could be multiple paths. If we look at the search space as a tree, we might be getting to that node many times over, and we are expanding a node more than once. So, if we want to deal with this, we must consider that the search space may be a graph, and that in this case the search tree may contain different nodes corresponding to the same state. These are examples of some search spaces which contain nodes more than once. Look at this search graph. This is node A, this is node B, this is node C, this is node D, and so on. There are two paths, two arcs from A to B, two arcs from B to C, two arcs from C to D, and so on. Now, if we unfold this as a tree, this is A, this is B, this is B, this is C, 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 C. So, there would be 8 nodes corresponding to D, 16 corresponding to E, and so on. So, if we have n nodes, this tree will have size of the order of 2 to the power n. So, the search tree can be exponentially larger than the search space. Tree search methods are not very good for such types of search spaces. So, in order to have an algorithm which can work efficiently when the search space is a graph, we need to avoid repeated state. So, there are different mechanisms that we could use. For example, we can choose not to return to the state we just came from. This is a very simple trick that we often use in 8 puzzle. When we expand a node, we do not expand a node and generate its successors, we do not generate its immediate parent. By this means, we can avoid some sort of duplication. A more sophisticated method is not to create paths with cycles in them. That is, when we expand a node to generate its successor, we check that the successor does not occur in the path from the node to the root. That is, we do not generate in the cycles. And the best way of doing this is not to ever generate a node more than once, by checking whenever we generate a state whether it was ever created before. Unfortunately, for doing this, we must keep track of all the nodes that were expanded ever, and we must check that this node was not expanded before. So, we need to maintain a list other than the fringe in the algorithms that we have, in the search algorithms. We usually call this particular list closed. So, closed is a list which keeps track of all the expanded node, and whenever we generate a node, we check whether it's not already enclosed. Now, this is the basic graph search algorithm, which is a variation of the basic search algorithm, tree search algorithm that we looked at earlier. So, fringe is a list containing the initial state. A fringe is often referred to as open. So, these are the nodes which are in the frontier of the search tree, which are candidates for expansion. It is called the open list or the fringe. Closed is another list. It is initially empty and it will keep all the expanded nodes. So, algorithm proceeds like this. We have a loop. If fringe is empty, that is no more nodes to expand, we return failure. Otherwise, we remove the first node from fringe and check that node is a goal or not. If node is a goal, we have found a goal state and we return by tracing the pointers and finding the path from the root to this node. Otherwise, if node is not a goal node, we put node in closed. Generate all successors of node, let us call them S. S is the set of successors of node. For all nodes M in S, if M is going to be generated, if M is not enclosed, then you add M to fringe, but if M is enclosed, you ignore M, right. So, we have modified the tree search algorithm for graph search. The basic difference is we have included this closed list which is initially empty. Whenever we expand a node, we put it in closed. When we generate a new node, we check whether it is already enclosed. If it is, then we do not generate it, otherwise we generate it. Now, let us look at a variation of breadth first search which we call uniform cost search. As we have discussed, breadth first search expands node according to its level by level. So, it expands nodes which are smaller number of steps away from the start earlier. However, sometimes arc costs are not uniform. So, instead of generating nodes level by level, we will like to generate nodes, those nodes earlier that have smaller cost from the parent. So, we might like to generate nodes in the order of their distance from the parent, and this is done by uniform cost search. In uniform cost search, when we put the nodes in the queue, we order the nodes by the path cost from the root to that node. Instead of, in breadth first search, what we do is that we maintain a queue for storing the fringe, that is, when nodes expanded, they are added at the back of the queue. In uniform cost search, we maintain the fringe as a priority queue. The priority of a node is its distance from the root, right? So, nodes are enqueued by the path cost, for which a priority queue can be used. The heap data structure is ideal for storing a priority queue. Now, we denote by Gn the cost of the path from the start node to the current node n. Gn is the cost of the path from the start node to the current node. We store nodes in the priority queue according to the value of G. And the algorithm expands the lowest cost node of the fringe. The algorithm can be shown to be complete. It is optimal or admissible, and it has exponential time and space complexity in the worst case. Let us look at, as an example, let us look at this search graph consisting of these 5 nodes. This is the start node, this is the goal node. In uniform cost search, we will start with the start state S, first generate A which has a G value of 1, then generate B which has a G value of 5. Then there are the candidates for expansion are G along this path with a G value of 13, G along this path with G value of 10, C along this path with a G value of 18. So, this is smaller, so we will expand this G which has a G value of 10, right, and then we will try to find out which is the shortest path, and then we will expand this node goal, and we would have found the shortest cost path from the start state to the goal state. As a result of breadth first search, we can find the smallest length path from the start to the goal. If we do uniform cost search, we can find the minimum cost path from the start to the goal. Next, we will come to informed search. In informed search, we use heuristics about the problem domain. Uninformed search methods that we have looked at earlier, they systematically explore the state space to find the goal. They are not very efficient in most cases. We saw that the most of the time the complexities of the algorithm was ordered b to the power d, that is exponential in the length of the search path. Informed search methods try to improve problem solving efficiency by using problem specific knowledge. So, let us first try to see what we mean by heuristic. Heuristics literally means rule of thumb. This is a definition of heuristics by Jody Pearl. Heuristics are criteria, methods or principles for deciding which among several alternative courses of actions promises to be the most effective in order to achieve some goal. In informed search, we use heuristics to identify the most promising search path. Let us look at some examples of heuristic function. A heuristic function at a node n, which we will use for the purpose of the search algorithms, is an estimate. The heuristic function is an estimate of the optimum cost from the current node to a goal. We usually denote a heuristic function at a node n by Hn, which is the estimated cost of the cheapest path from node n to the goal node. For example, let us say we want to get a path from Kolkata to Guwahati. So, here we have a map. This is Kolkata on the map and this is Guwahati on the map, right? And the actual path from Kolkata to Guwahati might be this. An estimate, if we do not know what the actual path is, an estimate of the distance of this path is the Euclidean distance, or the shortest distance between Kolkata and Guwahati. Okay. So, this distance, the straight line distance between K and G, is an underestimate of the actual distance of the path from K to G. Let us look at the game of a 15 puzzle that we discussed earlier. This is one configuration for the 8 puzzle. This is a given configuration of 8 puzzle or 15 puzzle. Sorry, this is not, yeah, this is 8 puzzle, it's all right. So, this is a given configuration of 8 puzzle and this is the goal that we are trying to achieve. One heuristic for 8 puzzle is the number of tiles out of place. What is the actual cost to get from n to goal? We have to take a number of moves to get from n to goal, right? And that is what we would like to find out. However, it is not easy to look at this and say what would be the minimum cost path. But what we can easily do is find out the number of tiles which are not in their correct location. For example, look at 2 here. 2 is not in its correct location in state n. In order to move to its correct location, we have to move 2 at least once. Similarly, 8 is not in its correct location, 3 is in its correct location, 1 is not in its correct location, 6 is not in its correct location, 4 is in the correct location, 5 is in the correct location, 7 is not in the correct location. So, the heuristic at node n equal to 5, because 5 tiles are not in their correct location and we must make at least 5 moves to move them to their correct location. So, Hn, that is 5, is an underestimate of the actual number of steps required to move to the goal state. Another heuristics for 8 puzzle is the Manhattan distance heuristic. For example, let us say 2. This node 2 is not in its correct position. In order to move 2 to its correct position, we have to move to 1 position to the right. However, look at node 8. Node 8 is not in its correct position. It has to move to this position. To move node 8 to this position, we have to move 1 step down and 1 step to the left. That is, we need at least 2 moves. Okay. To move 6 to its correct position, we need at least 1 move. To move 7 to its correct position, we need at least 1 move. To move 1 to its correct position, we need at least one move. So, Hn in this case is 1 move for 2, 2 moves for 8, 1 move for 6, 1 move for 7 and 1 move for 1. That is, in this case it is equal to 6. So, this is an underestimate of the actual number of moves required to move from this state to this state. Now, we will look at another search algorithm which uses this heuristic information. Best first search is a generalization of breadth first search, where the fringe of the open list is maintained as a priority queue, and a cost function Fn is used which denotes the priority of a node. So, Fn is the cost function of a node which denotes the priority of the node. Nodes are put in fringe sorted according to the value of Fn. So, this is the modification of the basic search algorithm using the function Fn. Fringe is maintained as a priority queue containing the initial state. If fringe is empty, return failure. Otherwise, we remove the element with the highest priority from fringe. Let that be node. If node is goal, we return the path from initial state to the node. Otherwise, we generate all successors of node, put the newly generated nodes into fringe according to their F values. End loop. So, best first search is a variation of the search algorithm where fringe is maintained as a priority queue and nodes are put in the priority queue ordered by their priorities, which is denoted by the F value of a node. So, let us try to now look at different variations of best first search according to the function F that they use. The most simple algorithm that we will look at is the greedy search algorithm. In greedy search, we always expand the node with the smallest estimated cost to reach the goal. That is, the F value of a node is H value of a node. So, H is a heuristic function. The H value of a node is an estimate of the actual path cost from the node to reach the goal. So, we use Fn equal to Hn. However, this search algorithm, we can show that it is not optimum and it is not complete. So, this is an example of greedy method. We are starting here from the start state, which is Seattle, and our objective is to reach Boston. Now, so these are the arcs, so these rectangles are the cities and the arcs denote the cost between the cities, right. Now, if we do greedy search, we will evaluate a heuristic function at each of these nodes, and from Seattle we will move to that city which has a smallest H value to Boston. And in this case, suppose it turns out to be Reno. From Reno we go to Memphis, Memphis to say Atlanta, to New York, to Detroit and to Boston, and we get a path like this. However, greedy search may not always give us the optimum solution, which we can show. We will show it with some example at the end of this class. Next, we will come to A star search, which uses a slightly more sophisticated heuristic function. So, in best first search, Fn is taken to be equal to Gn plus Hn. We have seen that Gn is the cost to get to the node from the start state, and Hn is an estimate to get from the node n to the goal state. That is, Gn is the sum of the edge costs from start to n, and Hn is an estimate of lowest cost path from n to goal. Now, it is a theorem, and we will show that if Hn is admissible, then A star search, which uses Fn equal to Gn plus Hn as the priority function, it will find an optimum solution. And Hn is admissible if it underestimates the cost of any solution which can be reached from node. So, an underestimating heuristic function is an admissible heuristic function which gives an estimate which is a lower bound of the actual cost. Now, this is the algorithm A star for graphs. So, this is algorithm A star for graphs. This is a generalized A star called graph search. Let us go over this algorithm. Open, we maintain two lists, open and closed. Open maintains the nodes on the frontier of the search tree, and closed maintains the expanded nodes. Initially, we put the start state S on open. We also keep with every node a pointer to its path from the root, that is, we keep a pointer to its parent. So, open contains the tuple S nil. So, then we have a loop while open is not empty. We remove from open the node NP, which has the minimum value of Fn. We put NP on closed. If n is a goal node, we return success and we return the path P. For each edge connecting n and m with cost C, so n is the node that we are expanding and we find its successors. For each successor m of node n, we check if m is enclosed with a path q, with a parent pointer q. So, if mq is enclosed already and the current path, the path from n is p. So, the path for m, the current path for m is p concatenated with e. So, if the cost of the path PE is cheaper than the path Q, then the current path to M is cheaper than the path that we have already got earlier. So, we will consider this path. However, otherwise the earlier path that we obtained for M was cheaper and we will throw away the current node M. So, if MQ is already unclosed and P concat E is cheaper than Q, we remove N from closed and put M P concat E on open. Otherwise, if MQ is not enclosed but MQ is on open and P concat E is cheaper than Q, we replace Q with P concat E. Otherwise, if M is not on open, we put M and the path P concat E on open, and when open is empty, we return failure. So, this is the generalized algorithm for A star search. We will show that A star is an optimum algorithm. That is, it is also optimally efficient. It gives the optimum solution and it is also the optimally efficient algorithm. A star is complete. However, the number of nodes searched is still exponential in the worst case, unless the heuristic is extremely accurate, logarithmically accurate. Now, we will show that we will try to find out the condition on Hn for which A star gives you the optimum solution. So, the property of admissibility is that provided a solution exists, the first solution found by the algorithm is an optimum solution. If A star can guarantee this, we will say that A star is an admissible algorithm. So, in order to show that A star is admissible, we will try to find out the conditions under which A star is admissible. Firstly, the state space graph should have these characteristics. Every node must have a finite number of successors. In the search tree or search graph, every node must have a finite number of successors. Every arc must have bounded cost. That is, there exists an epsilon such that every arc cost is greater than epsilon. And thirdly, we have a heuristic function Hn, which is always an underestimate of the actual cost, actual optimum cost from n to goal. We denote that by H star n. H star n is the cheapest cost of a path from n to a goal node, and our heuristic function Hn must be an underestimate to H star n. Now, it can be shown, we will not go into this proof, that A star is optimally efficient. What do you mean by optimally efficient? For a given heuristic, given a particular heuristic function, let us say h, of any optimal search algorithm that you could have, any optimal search algorithm that expands search paths from the root node, it can be shown that no other optimal algorithm will expand fewer nodes than A star on the average and still always guarantee finding a solution. Okay. So, A star is the optimally efficient algorithm. Secondly, we will consider a heuristic function which has the monotonicity property. That is, along any path, the f cost never decreases. The f cost of different nodes along a path can only increase, it cannot decrease. So, many heuristic functions Hn satisfy this monotonicity property. However, even if the heuristic function does not satisfy this property, we can easily enforce this property if we have an underestimating heuristic function by doing the following trick. Suppose we have a node n and m is a child of n. Okay. So, Fm is normally Gm plus Hm, and at node n we have Fn. Now, we can say that we will use as Fm the maximum value of Fn and Gm plus Hm. That is, if Gm plus Hm is smaller than Fn, we will use Fm equal to Fn to ensure that the monotonicity condition holds. We can do this because the f value of a node is an underestimate of the cost from start to goal through this node, right. The f value of this node m is an underestimate of the cost from start to goal through n and m, right. So, if Fn is an underestimate of this cost, we can also use Fm here without sacrificing the admissibility condition. Now, let us look at the proof that A star is admissible, that is, A star always finds an optimum path to the goal. Suppose G is a goal state and F star is the optimal path cost for the algorithm A star. So, G is we have the start state S, G is the nearest goal for which there is a path whose cost is F star. And suppose we have this other goal G2 which is suboptimum, and there is a path from S to G2, and the cost of this path is greater than F star. Now, we will try to see whether, we will try to show that it is not possible that A star algorithm will find G2 first before it finds G. In order to prove this, let us start with the opposite contradiction, that suppose A star has selected G2 from open for expansion. So, suppose A star has selected G2 from open for expansion. Now, we have our node, this is my start state, this is G and this is G2. Suppose if G is not on open, there must be at least another node on this optimum path which is on open. So, the node n of the optimum path must be on open. Now, suppose our algorithm A star has selected G2 for expansion and not selected n. Thus, Fn, so if n is on the optimum path from S to G, then Fn must be less than equal to F star. That is, F star is the cost of the optimum path from S to G, and Fn, which is an underestimate, must be less than equal to F star. Now, if G2 is chosen for expansion and n is not chosen for expansion, it must be the case that f of G2 is less than equal to Fn, that is, Fn is greater than equal to Fg2. Now, because G2 is a goal state, f of G2 is simply G of G2, because h value of a goal state is 0. Therefore, it follows from these three conditions that Gg2 equal to Fg2 less than equal to Fn less than equal to F star, that is, Gg2 is less than equal to F star, right. So, if A star has to select a goal node for expansion while the actual optimum goal has not yet been selected, it must be the case that G of G2 is less than equal to F star. But this is a contradiction, because we just said that G2 is a suboptimal goal. So, this cannot happen. That is, when A star selects a node for expansion, it must be and that node happens to be a goal, it must be an optimum goal state. So, this is a sketch of the drawing. So, this is our S, this is G, and this is the node on this optimum path which is on open when G2 is selected, and we just showed that Fg2 equal to G of G2, which is greater than G of G by a resumption which has to be greater than equal to Fn. So, this cannot happen. Therefore, A star does find the optimum solution. Now, we have seen that A star is complete. Now, we want to A star is optimum. We have to show that A star is complete. Now, suppose G is an optimum goal state. What are the conditions under which A star is not complete? A star will not be able to reach G only if there are infinitely many nodes for which Fn is less than equal to F star. A star only selects for expansion those nodes whose F value is less than equal to F star. Okay. So, A star will not be able to get to the goal node if there are infinitely many such nodes. This can only happen if either we have a node with infinite branching factor, or we have a path with finite cost but infinitely many nodes. The first condition, a node with infinite branching factor, cannot happen because we assumed that the branching factor is finite. The second condition cannot happen because we assumed that all arc costs are bounded and they are always greater than epsilon. So, there cannot be infinitely many nodes on the path. Thus, A star is complete. So, this lemma states that A star expands A star expands only those nodes whose f value is less than or equal to f star. In fact, A star expands nodes in order of increasing f values. So, we start from this node, the start state, and A star expands node with increasing value of f values. Now, let us look at properties of heuristic functions. Suppose we have two heuristic functions h2 and h1. We say that h2 dominates h1 if the value of h2 at any node n is greater than the value of h1 at that node n, and we can show that A star will expand fewer nodes on average using h2 than when using h1. Now, let us show the proof, sketch the proof of this. A star with h1 as the heuristic function expands every node for which fn less than f star. So, every node for which fn less than f star will be expanded. Some nodes where fn equal to f star, some of these nodes will be expanded. A star with h2 as the heuristic will expand all nodes with f2n less than f star. So, if h2n is greater than or equal to h1n, the nodes which A star with h2 will expand must be a subset of the nodes which A star with h1 can expand. However, depending on the execution, those we might have some leeway for those nodes where fn equal to f star, but on an average, because A star expands those nodes whose h value is less than f star minus gn. So, if h2 is greater than h1 at all nodes, then A star with h2 will expand fewer nodes. So, A star with h1 is preferred to A star with h1, A star with h2 is preferred. So, so long as the heuristic is an underestimating heuristic, we prefer that heuristic function which gives a higher estimate. Suppose we have identified a number of underestimating heuristics for a problem. There are h1n, h2n, hkn and so on. So, we can combine these multiple heuristic functions by taking the maximum of h1, h2 and hk. So, we can find the values of h1, h2, hk at that node, and since all of them are underestimates, we can take that value which is maximum, and this happens to be a more powerful non-overestimating heuristics. Now, we will quickly look at a variation of A star which is iterative deepening, which is similar like iterative deepening search, but instead of using a depth bound, we use a f limit. Initially, we start with limit, the f limit equal to the h value of the start node, and then we do a depth first search, and we prune any node for which f value of the node is greater than the f limit. We set that the next f limit to be the minimum cost of any pruned node. So, we start from node A here, we have to reach node D which is a goal node. We first set the f limit as 15 and we expand these nodes in a depth first manner. Then we set the f limit as 21, and then we expand these nodes, and then we change the f limit, and then we expand all the other nodes. So, iterative deepening S star can be shown to be complete and optimal. However, the space used, because we use depth first search, the space usage is proportional to the depth of the solution. So, it saves on space. The number of nodes expanded, it expands some nodes more than A star, but usually it is of the same order as nodes expanded by A star. So, in general, if there are lot of values, lot of possible f values in the search tree, IDS star can generate square of the number of nodes that A star generates, but where several nodes share the same f value, IDS star will typically expand a constant order of nodes more than A star. So, in 8 puzzle we have few values of f, because they are all integers, all the f values are integers, so few values. So, IDS star is quite efficient. In traveling salesman problem, each f value is unique if the path costs are real numbers, and number of nodes expanded will be order of n square, because it could be the case that at every iteration one more node is expanded. So, the total number of nodes expanded is 1 plus 2 plus 3 plus up to n, which is of the order of n square. And it is very difficult if we are using depth first search, we really cannot detect nodes which have been expanded before. So, it is not a very good choice if we have a search graph. Otherwise, depth first search is very attractive because the space requirement is small. So, we will stop this lecture by quickly running greedy search as well as A star on this graph. So, we start from start state from A. If we do greedy search, we will try to go to that node for which h value is smallest. Suppose we choose as h value the straight line distance from a node to the goal node. This is my start node, this is the goal node. In greedy search, from A we will go to B, from B we will go to E, from E we will go to G, from G we will go to the goal node H. And we get this path whose cost is 70 plus 15 plus 6 plus 8, that is 85, 91, 99. This path is not optimum. Now, let us take the same graph and run A star. We first expand node A, and then we add node B to the fringe whose G is 8, H is 18.6 and F is 26.6. Then we expand B, and then we add C, D and E to the fringe. For C, the F value is 35.1. We put it in the fringe, we evaluate D, F value is 35.2, then we evaluate E with F value 27.5, then we expand E, add successors G and C, evaluate G, Gn is 84, Hn is 8.5, Fn is 92.5, we add it to the fringe, then we take C whose Fn is 41.3, which is more than the F value of C which we already have on the fringe. We discard it, and then we put expand C, add node F whose F value is 37, we put it in the fringe, then we expand D which has no children, then we expand F, add nodes G and H to the fringe, we evaluate G whose F value is 42.5, we replace the previous F value, then we evaluate H whose F value is 39, we put it in the fringe, we expand H which is a goal node, and we have found a goal whose cost is 39, which is better than the cost of 99 which we found in the greedy search. And this is the optimum path to this goal node. Okay. So, we stop today's lecture and we will look at the questions in the next class. Thank you.